All right, we were in the middle of 9.4 when we left last time, and we had taken a look at factorial notation. We had talked about counting methods. This was the first one, the fundamental principle of counting. And we did our example for that one. And then we had talked about permutations of like objects and gave an example, I think, with starburst. And I mentioned last time that I would give you some other examples of things that are like this that aren't food. We can do lots of examples with candies. I mean, like, that's fine, and it's a good example, but that's not the only thing that applies to this. An example of doing things with permutations of like objects has to do with the way, one example has to do with how the Olympics are run or swam or counted when you have multiple what are they called, rounds of an event happening, right? So let's say, for instance, you're wanting to figure out who's the best swimmer in the freestyle 100, right? Well, you can't put every country in the pool at the same time, right? It doesn't work that way. And so what happens is you have these different heats that happen, right? So many of them will be in the pool at one time, and you take the top one or two people, whatever it is, it's usually the top two or three, actually, the top two people from that heat. And then you do the same thing again. You take the next two people from the second heat and take the next people from the second heat. It doesn't matter if you're one or two. As long as you're one of the two of them, you're in, right? It's indistinguishable. You just placed to get into the next round. That's an example of one. There's an example that you're going to see in your group work or homework, I don't remember, and they're running flags up a flagpole, and they're indistinguishable because the colors are indistinguishable with flags. Right? It doesn't matter if you have red flag number 1 or red flag number 4. You can't tell the difference when they're on the flagpole, right? When they're putting multiple flags, sort of like pennant kind of flags, not flags like country flags or state flags on there. So there's some other examples. I think there might be one that shows up that talks about seeing or counting types of cars, but only counting them by their make, not by their model, right? So the make is are they a Toyota or are they a Honda or are they a Ford? And so you're only looking at that style of a car, not whether it's a Ford F-150 or a Ford Taurus, right? You're looking specifically just at the broad categories and you're indistinguishing something else. You can do the same thing if you were looking at this for male, female, right? If you only cared about the order of people based on their gender or based on their classification or based on some criteria, just because the people themselves are different people, if all you're looking at is one specific aspect about them, it's like this. It's a permutation of like objects, okay? So there's a lot of categories of things that fall into this. There's two other kinds that we're going to look at today, though. Permutation of unlike objects, and then there's going to be combination. So in a permutation of unlike objects, all the objects are distinguishable. Okay, they're all uniquely different. So the way that this works is that we are taking n objects and we are choosing r of them. So when you're taking a look at this notation, that's what you're seeing here. The first n is how many we are choosing from. So choosing from n, and I'm going to use objects in quotes because, objects could be people. It's not trying to distinguish persons or places or things, or it's not like that. It's just whatever you're choosing from, it's those things. And then r is how many you choose. And you see that factorial notation showing up yet again. So on the top, it's the number of choices you have, things you have to pick from, okay, n factorial. And on the bottom, you have n minus r, which is actually interesting because r would be how many you're choosing. So n minus r would be the number you're not choosing. Okay, so down here on the bottom, these are the ones, n minus r actually is the number that are not chosen. And the reason that we end up dividing by that quantity is because it doesn't matter what order you pick the things you don't pick, right? They just stayed in the basket. I don't care what order I would have picked them in. They weren't chosen. It doesn't matter. And that's why they get divided out, is because they are irrelevant to the counting strategy that you already had from before with the things you did choose. All right, so we're going to do an example. 30 contestants put their names in a hat for a raffle. First place wins $100, second place wins $50, and third place wins $25. And how many different ways can prizes be awarded? Okay? So everybody's got their name in the hat. There's 30 people. 30 people's names are in a hat. We're going to draw one person's name out, and that person wins the grand prize of $100. Make sense? Then we're going to reach in, we're going to grab another one. That person wins the second prize of $50. Draw one third name, and the third person wins $25. And the other 27 people in the basket, we don't care what order we would have selected them in because we're not selecting them. Okay? So if I'm thinking about this with this notation, how many am I choosing from? How many names are in the basket? 30. And how many of them are going to win something? 3. So this is 30p3. Now I'm going to talk about why it's a permutation in a second, but let's do the calculation so we can see how it works first. So it's 30 factorial on top, okay? And then on bottom, you can think of it in terms of a formula. It's 30 minus 3, that's fine. 30 minus 3 is 27. Or you can think of it in terms of a concept. It's the things that are not chosen. Well, I don't choose 27 names. There are 27 names left in the hat, basket, whatever. Now let me remind you how we do this. We do not put 30 factorial on your calculator because if you do, your calculator is going to tell you it's too big. It'll either do a memory overflow if it's big enough, or it'll sort of truncate it, which means it shortens it, puts a decimal in there and turns it into scientific notation, which means you lose accuracy. That's not what we want. So what we're going to do is we're going to write out the 30 factorial until it matches with what's on bottom. So it's 30, 29, 28, and at 27 factorial, I stop because it is a perfect match with the 27 factorial on bottom. I'm able to cancel those out completely because they represent the same quantity, 27 times 26 times 25 all the way to 1. So I get to cancel them out completely, and I need to multiply 30 times 29 times 28. So somebody grab something and multiply 30 down to 28 for me.
23,520.
I think it's bigger than that, a little bit bigger. There might be a typo in what you entered. 24,360, yeah. So there are 24,360 different ways this can be chosen. Now, I didn't make a big issue of it, but let me mention it now. Do you see this thing in red that says order matters? It's in bold type. It's in red. It must be important. And I didn't say anything about it, did I? Well, here's what the deal is. The order matters on this problem because it matters whether you were drawn first, second, or third. Your prize was different, right? That's why the order mattered. The order matters on a particular problem. We have a permutation. In permutations, order matters. Now, we're about to do another formula here, but let me just read this question so you can see the nuanced difference when order doesn't matter. In example 5, there are 30 contestants. They put their names in a hat for a raffle, and 3 people win $75. And how many different ways can the prizes be awarded? Well, now it doesn't matter whether I was picked first or second or third. My prize is the same every time. Can you see the difference? Right? All the prizes are equal, which means the order in which I was drawn, if I received a prize, right, it doesn't make any difference. Whereas on the first one that we did, it did make a difference. All right, so let's take a look at the formula, and then we will look at this particular problem. In this counting strategy, you notice the notation looks very similar. I have an N and I have an R, and they're in like the same place, but there's a C in between them. C stands for combination. And over here, I have much the same as what I had before as well. I have N factorial on top, that matches. I have N minus R factorial on bottom, the number that weren't chosen, that matches. The new part that I have on bottom is R factorial. And the reason I have R factorial on bottom now is because the order that I draw the winners in doesn't matter either. So I have to divide it out. It's just like with my starburst example. I divide out the things that you can't distinguish between. I can't distinguish between all the people's names that are still in the hat and didn't get drawn. That's why it's divided out. And I can't distinguish between all the people's names that I drew and they get prizes because they have the same prize. They're indistinguishable. Okay? So I'm dividing both by the number of things I chose and the number of things I didn't choose when I'm doing a combination. And the answer will be smaller because I'm dividing by additional stuff. So when I do a combination, I get fewer values. I get a smaller number than I do when I'm doing the same, equitable permutation. So we have our 30 contestants. It's a combination because their prizes are the same. The order I draw them in doesn't matter. So it's 30, choose 3. The 30 factorial goes on top. The number of non-winners, aka losers, is 27. So that's on bottom. But the number of winners is on bottom as well, 3 factorial. I do this problem the same way. I'm going to write my 30 factorial down till I get to 27. 30, 29, 28, 27. And once it matches the largest thing on bottom, I do stop. And then I write out the other piece entirely. If you don't want to write out the times 1, you wouldn't necessarily have to. But 3 factorial is 3 times 2 times 1. So the 27 factorials, they cancel, just like last time. But the 3 and the 2 also will reduce with what's on top. Now, if you wanted to multiply the top and multiply the bottom and use your calculator to divide at this point, you certainly could. But they will always divide out as well. 3 will divide with which of those 3 numbers? The 30. The 3 will divide with the 30 and give me a 10. Your 2 actually has choices. You can either divide the 2 with the 10 on top or the 2 with the 28. Which one do you want to do? 28. Awesome. So we're going to mark the 28 out, the 2 out, and put a 14. And then we're going to take our calculator. We're going to multiply 10 times 29 times 14. What are we going to get? Something smaller than before. 4,060. There are 4,060 ways this could happen. There's not as many because I lost the specificity of the prizes. The prizes were all the same. So it didn't matter the order I drew the winners out in. Yeah.
So it would be okay if we didn't cancel out.
Mm-hmm.
If we just
Yeah, if at this point, let's say you got down to the point here where you had 30 times 29 times 28. You'd already canceled the 27 factorials out and you had 3 times 2. If you multiply the top together here, multiply the bottom together here and do the division, that's fine too. Okay. You'll get the same thing. Yeah, you could do that. Okay, any other questions so far? All right, so what we're going to do next is we're going to encounter a variety of questions that don't tell us how we're supposed to answer them. And we have to figure out which of those strategies to use. Is it fundamental principle of counting? Is it permutation of like objects? Is it permutation of unlike objects? Or is it a combination? There's 4 choices. And sometimes you can use one of 2 of them and it will still give you the same answer no matter which 2 you use. There are cases where that happens. But let's do an example. So we have phone numbers in a large business. OBU would be an example. If you looked at any of the numbers at OBU, it's 405-585. That's our numbers. This one is 405-767. Okay? So we have a business and all the phone numbers look like this. How many different phone numbers are possible? Well, those last 4 places, those X's are numbers, right? How many number options do we have in each one of those places? 10. There's 10 numbers, 0 through 9, right? We have 10 choices in each one of those places. This problem is a fundamental principle of counting problem. And the reason is because I can use that number again and again and again. So when I was doing those people who were drawing out the names, in the prize raffle thing, once I drew their name out, they didn't get to go back in the basket and get another prize, right? That's why that one doesn't have a repeated number showing up like this. It actually went down every time. It's because I had fewer people in the basket I was drawing out. In this case, I don't have to have, once I put the number 3 in here, like let's say that the next digit's a 3. Well, that doesn't mean that the next digit after that or the next digit, they could repeat. It's okay for the numbers here to repeat. So this one's fundamental principle of counting. We would multiply these together. There's 4 X's at the end, 4 empty places of digits. And if I multiply this together, what is 10 times 10 times 10 times 10? It is 10,000. There are 10,000 phone numbers. That's a lot of phone numbers. You probably don't need that for most companies, right? Probably not. 10,000 different phone numbers. Okay, this next one has two different ways we could do the problem. A worship team practices 8 songs on a Wednesday night for the Sunday service. If the worship minister plans to choose only 5 of the 8 songs, in how many ways could the songs occur? So they're not going to sing all 8 of them, right? They're going to only sing 5 in their worship set, but they've practiced 8, and he's going to select 5 of them. So this says, its phrasing is very specific. It says, in how many ways could the songs occur? That's telling you that the order matters. Like they told you that. Do you see how that language says that to you? It matters, the order. Now, from a contextual standpoint, you should probably have an idea that that would matter anyway. If you've been in any kind of a setting where there's been music going on, especially music you're worshiping to, there's a specific order and it makes a difference, right? There's a crescendoing, and you usually have your praise and worship stuff, and then when you get toward prayer time, you get the quieter stuff, that kind of thing happens, right? And if you switch that all out of order, it's different. The environment is affected, so the order is different. This one, the order matters. So if an order matters, we're actually looking at something that would be a permutation. And these are unlike objects because the songs are all different. Make sense? So one way of doing this is a permutation of unlike objects. So I have 8 songs. Whoops. I'm doing a permutation and I'm going to choose 5 of them. So on top I have 8 factorial. On the bottom, what I have is the number of songs I don't choose. How many am I not choosing? 3. So I'm going to write my 8 times 7 times 6 times 5 times 4 times 3 factorial out with the 3 factorial on bottom. These cancel. And then I would actually multiply those remaining digits. 8, 7, 6, 5, 4. So 6,720 ways that I could set this worship set up with those conditions. You could actually do this one as well with the fundamental principle of counting. And you could think of it as though, well, I just need to pick one song. There's 8 songs I can pick from. And then I need to pick a next song, and I'm not repeating a song. So there's 7 songs to pick from. I need to pick a third song. There's 6 songs. A 4th song, there's 5 songs, and a 5th song, and there's 4 songs. So you could also think of this as a fundamental principle of counting problem, and sort of as a going down the list, I'm actually choosing my worship set from the available options like that. I'll still get 6,720 ways, of course, but it's sort of a different perspective that's equally right. Okay. We have talked about a standard deck of cards before. We're going to do it again here. So we have a standard deck of 52 cards. So remember, 26 red, 26 black, 13 clubs, 13 diamonds, 13 spades, 13 hearts. Hearts and diamonds are red, clubs and spades are black. We have an ace and a king and a queen and a jack of every suit. And then we have number cards that go 2 through 10. Nod your head if you remember us talking about this in class. Okay, we did talk about this in class. If you're not very comfortable with a deck of cards and you want to come and talk with me a little bit more about cards, we can do that. That's not a problem. I'm not trying to give a context that's unfamiliar, but it does provide really nice questions, so it's a good place for us to get some good questions from. So the first question is, how many different 5-card hands can be dealt? So we have a 5-card hand, and the deal with cards is this. I don't care whether you've played Go Fish, or whether you've played Rook, or whether it's Slapjack or War, or it doesn't matter. Every game works like this. Somebody deals all the cards out, and what's the first thing you do when you pick them up? You look at them, and then what? You put them in some kind of order. And the order is usually based upon the game, right? Maybe you're grouping colors together. Maybe you're grouping suits together. Maybe you're grouping numbers together. If you're playing phase 10 or a game of that nature, you're constantly changing how your groupings are in the middle of the game, depending on which round you're in. But the first thing you do is you regroup the cards. Agreed? What that means is that the order in which they were dealt didn't matter. It mattered whether you got the cards or whether Chesney got the cards or whether Taryn got the cards, but your cards in your hand didn't matter if you got them first or fourth, right? Because the first thing you did is you picked them up and you reorganized them. So if the order doesn't matter, what kind of a process are we working with? A combination. Yeah, Avery's right. It's a combination. So if we're not working with something where the order matters, we're working with a combination. So all of these problems that we're about to start with on the cards are going to be combination problems. Okay? So this one says we have 52 cards. It's a 52 card deck, and we're dealing 5. So there are 52 cards to choose from, and I'm being dealt 5 of them. So as I set this up, I have a 52 factorial on top, and I have the number of cards I don't get. So I get 5. We usually write that at the back, but you can write it wherever. 5 cards you don't get, or you do get. How many cards do you not get? 47. There are 47 that are not dealt to you. So the denominator is how many you don't get or don't choose, and how many you do get or you do choose. So I'm going to write the 52 out to 47. 52, 51, 50, 49, 48, and 47. On the bottom, I still have a 47, and then I have 5, 4, 3, 2, and 1. So the 47s cancel. They're done. Again, so like Kate Brown asked, could I just multiply these together on top, multiply them together on bottom, and get that answer? You probably can on this one. Sometimes the numerator is still too big to do that on that, but you can also reduce them. We're going to do the reducing. So if I take the number 5, which one does it nicely divide with? 50 to give me 10. How about the 4? Pick something. You've got options.
48.
4 and 48 gives me a 12. How about my 3? I actually have options on that one too. Yeah, the 12 again if you wish. So the 3 would go into 12 4 times. We got options on the number 2. Which one do you want to divide to? 2 and 4? Okay. So we'll do the 2 and the 4, which gives me another 2 on top. So I have 52, 51, 10, 49, and 2. What do we get?
980.
I think you might have done something wrong because it should be much bigger than that.
2,598,960.
Yeah. 2,598,960. Did you figure out what happened, Kate Brown? Oh, you left the first 2 off. Yeah, well, that will do it. Yeah, we need all of them. So there are 2.5, almost 2.6 million different hands of cards. Okay, this is why you see cards used so much in games, is because you can get a different game every time very easily. Because you got 2.6 million different ways this can happen if you have 52 cards. Some games even have more cards than that. Some have fewer, but yeah. So this is the different hands of cards. There are 2.6 approximately million hands of cards. Now, let's take a look at what happens if we identify some certain specific features. Let's say we want our hand to only have diamonds. Okay, so only diamonds in our hand. How many diamonds are there? 13. Right? Order doesn't matter, so I'm still working combinations. I'm going to do that on all of these. And how many cards am I going to have in my hand? 5. So this is 13C5. So 13 factorial on top. On bottom, how many cards do I not get? I get 5. So how many do I not get? 8. So I have 8 factorial and 5 factorial on bottom. So I'm going to multiply my 13, 12, 11, 10, 9, and 8 on top. I have 8 on bottom, and then 5, 4, 3, 2, and 1. So 8 factorials cancel. This one's actually really nice because some things pair up nicely. If you notice the 5 and the 2, what's 5 times 2? 10. That's something that's on top. And what happens with 4 and 3? Yeah, 4 and 3 makes 12, which is on top. You don't have to pair them up like that to do that, but they're nice that way. What is 13 times 11 times 9?
1,256.
1,287. Okay, that's a lot. 1,000 is a lot, but it's nowhere near the 2.6 million we just got a minute ago, right? Way less likely that you're going to get this than just anything at random. So that's what's happening on C. We're saying, okay, then, what's the likelihood that you really do get a hand of all diamonds? Okay, so we want 5 cards that are all diamonds. By the way, a hand that's all the same suit is called a flush. Okay, so that's where that language is. It's a diamond flush. So what we want is we want the number of ways that we, win compared to all possibilities, right? This is a probability. This is what we're finding. Win compared to all. I'm going to leave it like that. Well, in this case, this means we get all diamonds on top. And this is any option on bottom. Well, that's what we just did on parts A and B. All diamonds was part B. That was the 1,287 option. Anything happening was the 2,598,960. So grab your calculator. We'll do this we'll do this correct to 4 decimals. 4 decimals seems to be the going number they usually use on these in your books. So divide 1,287 by 2,598,960. It is small.
0004.
Close. I have a 5 on the end. Is it a 5?
Yeah.
Okay, 0.0005. If you want to think about, well, what is that as a percent? You could move the decimal a couple of times and you could say, okay, well, that's 0.05%. It's like never going to happen. Not never, right? But it's very uncommon. This is very difficult to pull off, getting a hand that is all diamonds. Okay, so let's try another example. We're going to do a group of students. They're 7 seniors, 5 juniors, 3 sophomores. And we're going to create a committee with those students. So we want the committee to consist of all seniors. And it does say probability, which means we're going to need to find 2 things. We're going to need to find, well, let's just write out what this is. So the probability, like we did the last time, is the number of ways, in this case, that it's all seniors. And this is any option or any grouping. That's what we have to do when we do probability. The number of ways we get what we want, in this case, all seniors, compared to the number of ways that anything can happen. So let's call this part A on top. Oh, we already have A, don't we? Because we're on A. Let's call this 1 on top and call it 2 on bottom. 1, we're going to try and get all seniors. Okay. How many seniors are there? 7. How many are on my committee? I mean, how many people are supposed to be on this committee? What's it say? 3. So we have 3 that we're selecting. So there's plenty of seniors to pick from. There's 7 of them, right? So there's 7 factorial on top. It's a committee. Committees are also combinations. And the reason they're combinations is because it doesn't matter what order you put on the committee, you're still on the committee. If you were selecting like a president, a secretary, and a treasurer, that's not a committee. That's officers. Do you see the difference? This is a committee. Doesn't matter the order they're selected. That's why I'm using combinations. So how many are not selected? 4 factorial. How many are selected? 3 factorial, right? So I'm going to write my 7, 6, 5 times 4 factorial to my 4 factorial. And then 3, 2, and 1. 4 factorials cancel. What else cancels? Yeah, the 3 and the 2 make 6. So all I have on top still is 7 and a 5, which gives me what? 35. There are only 35 ways that I can choose 3 seniors. Okay, so my numerator up here now that I just got is 35. I'm going to do step 2, which is any committee. Okay, so any committee means any of these people can be on it. How many of these people am I referring to? What does it say? I'm still selecting 3 people, but how many people do I have to choose from? 15. There are 15 people that are described here, right? By their classification. There's 15 choices. And I'm still selecting 3 people. So I have 15 factorial. How many are not going to get picked at all? 12. And 3 are. So my denominator has my 3 and my 12 in it. How many are and are not getting picked? I've got 15, 14, 13, and 12 factorial with another 12 factorial, and then 3, 2, and 1. 12 factorials cancel. 3 cancels with 15 to give me 5. 2 will reduce with the 14 to give me a 7. And what do I get when I multiply 7, 5, and 13? $455. So we have 455 up here. You can simplify this in terms of a fraction. If you do, notice they both had a 7 and a 5 in them. Do you see that? The only thing that happened is there's a 13 down here. So if you reduce this in fraction form, it's 1 over 13. If you do it in decimal form to 4 decimals, that's okay too. So if we do this in decimal form, what I end up getting, I'm going to spoil the fun so that we can get this finished, is 0.769. 0.0769 probability. Again, not very likely, but it's way better than my choosing my diamond flush. Yes, tomorrow. If I don't, it'll say something different. So for what we're working on in the book, we're going to go with 4 decimals. If I wanted you to do something different on your homework or group work, or that's not what I meant to say, on your test is what I meant to say, then I would tell you something different. So 4 is going to be our default for probability. Yeah. Thanks for checking.
If we just do one or the other, are we going to get it wrong if we only do a fraction or decimal?
Oh, either one would be fine here. Either of these options are good. Okay. Either a reduced fraction or a decimal expansion. Yeah. For the problems over here, the fractions are so big on it doesn't work very well to do this anyway. So decimals are just what makes sense. Here you kind of have choice. Okay, last question real quick. What's the probability of having no seniors? Okay, this phrase no seniors means that I would have what? I would 0 seniors, but what would I have instead? I'd have all juniors and seniors, or juniors and sophomores, right? They have to be all juniors and sophomores. So this phrase right here is equivalent to saying that I have only juniors and sophomores. So my winning in this case is getting juniors or sophomores on my committee only compared to all. And I already did the denominator, right? I already know the all. It was 455. I don't need to do that again. I already did that once. I just need the top part now. So how many juniors and or sophomores are there?
8.
There are 8, and I need 3 of them on committee. So I have 8 on top. How many are not chosen? 5. How many are chosen? 3. So this is 8, 7, 6, 5 factorial over 5 factorial, and then 3, 2, and 1. So the 5 factorials, they cancel. What happens with my 3 and my 2? Cancel with the 6. So I end up with 8 times 7, which is 56. So up here, 56. I won't write the fractional one. I don't think I have that one written down. But you could, right? Like it would be okay. They will reduce. They both divide by 7, but they don't actually divide out as cleanly, as fully as the other one. As a decimal expansion, the approximation here is 0.1231. It is still a lot likely, right? You're probably going to have some sophomores, juniors, and seniors on the committee as a general statement. You don't have a guarantee of who's going to be on there. It's about a 12% chance. We'll stop there.